All right, so the first lecture, or lecture 0, is about calculus review. I will go over some of the top level informations about calculus that you have learned in Calculus 1 and Calculus 2. I'm not talking about multivariable calculus in this lecture at all. There's only one topic that we need the knowledge of multivariable calculus, and that is the solution method involving exact differential equations where you need to use partial derivative. And that's it to the extent of multivariable calculus. But for calculus review, I want to go back and recall the definitions of derivative using limits, to review and apply differentiation rules, some of the basic differentiation rule technique that we can use, look back to the fundamental theorem of calculus, and revisit some basic integration techniques. Okay. I'm just going to give you, again, the higher level information and not going to do any work related to in this method, right? Because we have all the time in Calculus 1 and Calculus 2 go over all the example for the techniques that we learn. But eventually, when we get to the solution method, you will encounter this type of rules and techniques again. And then when it's come up, like those are the example that we can work together to strengthen the knowledge of differentiation rules and integration techniques. So in calculus, there are two branches of calculus, differential calculus and integral calculus. Right? And the word calculus is the Latin word for pebble. Right? Back in the day, Roman people use pebble to do calculation, to do addition, subtractions, and therefore the word calculus. And again, there are two branches of calculus: differential calculus that you spend a lot of time, like 3/4 of calculus 1, to work on. Differential calculus talk about tangent problem and velocity problem. There's a lot of good information in this differential calculus when you talk about limits, when you talk about differentiation. And also, after you learn differentiation, you use that to apply to some applications to derivative to find maximum, minimum, and to sketch the curve without using the calculator. So applications of derivative. And then the last quarter of calculus 1, you start looking at integral calculus. You ask the question, what is the area under the curve, and things like that. And move on to calculus 2. The first half of calculus 2, you learn a bunch of integration techniques allowing you to find the solutions of the integral or definite integral or indefinite integral using different technique. And the technique that you learn depends on the professor, but mostly you learn about just some basic integral technique, right? Just use basic formula, or you use integration by parts, integration by substitutions, integrations involving partial fraction decompositions. Those are the technique that you're going to encounter over and over again throughout the semesters of the course. So for integral calculus, you talk about area problem. You talk about different technique like integrations by parts, use substitutions, and integrations involving partial fraction decompositions. We're going to see all of this information again throughout the semester when we start talking about the solution techniques to solve differential equations. So first thing first, let me get to details of differential calculus. The first thing is definitions of derivative. So derivative of the function f of x using a different notation here that you have f prime or dy dx. It depends on how convenient for you to write this type of notations, but this notation right here, dy dx, is the Leibniz notations. Or you can use f prime, you can use them interchangeably, f prime, and this is the Lagrange notations. And for engineering people, they tend to use slightly different notations, although not many engineering people use this notation. This is called the Newton notation, and it has this notation. So x dot means the first derivative, so this is Newton notation. All right, so derivative of the function f of x denoted as f prime of x or dy dx. is the function whose values at x is. So you have f prime of x is equal to the limit of f of x plus h minus f of x altogether divided by h as h approaches 0, provided that the limit exists. Okay. So this part of the formula, this part right here, is called the difference quotient. You can write, try to understand this, is that calculate the derivative at each point along the function, so along the curve. Right? You set x to a specific value, x equal to a, x equal to c, whatever that is, right? Allowing you to calculate the derivative of the function as a given point. But overall, the derivative function is written as this form. Okay. So the derivative of the function f at a number a can be thought as, so these are the three interpretations of the derivative at a point in space. So this can be used to calculate the slope of the tangent line to the curve at the point. Right? It can be used to calculate instantaneous velocity at any time t equal to a. And it's also, in general, is the instantaneous rate of change when x equal to when x equal to a. So this plot, I have this 3 plots right here. Hopefully you have seen this similar plots before to illustrate the where you get the tangent line, right? How could you calculate the tangent line? The tangent line, of course, is a line, and the line depends on the slope and the y-intercept. So the slope is actually the derivative of the function at a given point. So you start out with 2 points. You have the point P right here, and you have the point Q right here. If you draw a line to these 2 points, and this is the line right here, right? This is called the secant line. Secant means cutting or to cut. Is a Latin word as well because it's cutting through the curve and it's through 2 points, right? So that's why it's called that's had the name secant line. And to calculate or to find the equation of the line, the first thing that you need to know to do or to calculate is to find the slope of the secant line. Okay? So the slope of the secant line is y2 minus y1 divided by x2 minus x1, things like that. In other words, you can use different notations here. You have x and a. So this is x, right? So this point corresponding to x, this point corresponding to a. And this is the change in y. So you have dy here. This is the change in x. You have dx here. And the secant line or the slope of the secant line has the same equation as the average velocity. That is dy over dx, right? So this right here means that the change of y over the change of x. Now, how could you find the equation of a tangent line through the point P? What you do is that you move the point Q closer and closer to P. Right? So Q right here, this is another Q, this is another Q. When you move the point Q closer and closer to P, that means the value of x approaches the value A. And eventually it's close enough so that you can find the slope of the tangent line. And the tangent means touching or to touch. So that's why it's that's the line, tangent line. And when you let x approach closer and closer to a, you have the limit definitions for derivative. And the derivative are used to calculate the slope of the tangent line. So this is just one interpretation to derivative of a function at a point. Right? And again, because the calculation of dy dx is for the slope of the secant line and also for the average velocity or the average rate of change, when you take the limit, you have the slope of the tangent line or instantaneous velocity or instantaneous rate of change. So they relate to one another like that. All right, so then after limits, after definitions of derivative, we move on to doing some work on using differentiation rules, right? You have multiple rule here. You have constant multiple, you have sum and difference, you have product rule, you have quotient rule, you have chain rule. Right? And later on, we have some common functions that we usually use to find derivative. Right? So for the constant multiple, when you take the derivative of the constant multiple, what you do is just take the derivative of the function and then scale that derivative using these constant c. So f prime, you're going to get f prime of x equal to c times g prime of x. Okay, so just say that if the original function is scaled by another function, c is the scale, right? You can make the graph bigger, you can make the graph smaller, and when you make that scale, the derivative will be scaled as the same constant, right? You have sum and difference. Derivative of the sum is sum of derivative. Derivative of the difference is difference of derivatives. So y prime is going to be f prime of x plus or minus g prime of x. Again, derivative of the sum is the sum of derivatives. Derivative of the difference is difference of derivative. Now for product rule, you have y prime equal to f prime times g plus f times g prime. Right. Now for quotient rule, the formula is kind of similar on the numerator, but be careful because that's going to be a negative in the middle, right? Divided by g squared, provided that g is different from 0 because you don't want 0 in the denominator. Okay. Now for chain rule, you have f, this is going to be a derivative of composite function. So g of x is the inside function, f is the outside function. Right? When you find the derivative using chain rule, you have y prime to be equal to f prime of g of x times g prime of x. Right. So it say that the chain rule is equal to the product of the derivative of the outside function and the derivative of the inside function. Okay. So that's some of the rules, some of the basic rules that you see that you encounter in calculus 1. And then you're going to use that to, you use the limit definitions, you use some of the basic rules to find the derivative of some common functions. And of course, not many people use the limit definitions to find the derivative anymore because it takes a lot of time and effort to do so. And therefore, your professor probably just derive one equations or two equations and that's it. And they just going to give you a bunch of formula that you're going to follow. But here are some derivatives of some common functions. Derivative of a constant is equal to 0, right? So f prime of a constant is 0 of any constant, right? When we talk about derivative, again, the interpretation is that what is the slope of the tangent line? What is the instantaneous rate of change? What is the instantaneous velocity? So for the constant function, this means you just have horizontal line. When you have horizontal line, the slope is always equal to 0, and therefore the derivative is always equal to 0. Now you have a power function, x to the power n, for n is a real number. You have f prime of x is equal to n times x to the power n minus 1. Okay. You have exponential functions. F prime of e to the x is only just equal to e to the x. For e is an irrational number equal to 2.71, something like that. Now, if the base is anything different from e, then you have f of x equal to a to the x is also again the exponential function. F prime of x is equal to a to the x times ln of a. Move on to ln of x, logarithmic functions. F prime of x is equal to 1 over x. And for log of base a of x, you have f prime of x equal to 1 over x times ln of a. You have trigonometric functions. So f prime of x, f of x equal to psi of x, f prime is equal to cosine of x, f of x equal to cosine of x, f prime of x is equal to negative sine of x. For tangent of x, the derivative is equal to secant square x. For cotangent of x, f prime of x is equal to negative cosecant square of x. For secant of x, the derivative is secant x, tangent x. And for cosecant of x, the derivative is negative cosecant x times cotangent x. So this is some formula. You have seen it before, hopefully, right? And again, we're going to see this over and over again throughout this semester. If you don't have any questions, let's move on to integral calculus. Again, I just want to give you the higher level information. Right? So in the first or the 3/4 of calculus 1, you talk about derivative, right? When you have a distant function, you take derivative, you have the velocity functions. So this is derivative. And with the velocity function, take derivative, you have acceleration functions. Now, in the last quarter of calculus, when you start looking at integral calculus, you talk about area problem to find definite integral, but also the process, the reverse process of derivative is called antiderivative. If you are given an acceleration function, when you take antiderivative, you get back the velocity function. Take another antiderivative, you get back the distance function. So this is the process of antiderivative. In here, this is antiderivative. Right, be careful with the directions of the arrow. You have a forward process using derivative, and you have the backward or the reverse process using antiderivative. And there are two parts to fundamental theorem of calculus. And because there are two branches of calculus, so differential calculus and integral calculus, and these two branches get connected together using the fundamental theorem of calculus. So a fundamental theorem of calculus part 1 is that let f be a continuous function on the closed interval ab, then the function is defined by this capital F of x equal to the definite integral from a to x, for x is the variable. Okay, you can actually vary the value of x here, of f of t dt. So this function is also continuous on AB and is differentiable on the open interval AB, and you have that f prime of x or df dx or d dx of the functions from integral from a to x of f of t dt. Okay, so this first part say that if you take derivative on the antiderivative, in a way, it's easier to say it this way, right? That derivative and antiderivative cancel out, right? And therefore, the derivative, this is a notation for antiderivative, they kind of cancel out and you get back the functions f, but in term of x. So that's the first connection between differential calculus and integral calculus. Derivative apply on the antiderivative. Now, for the second part of the fundamental theorem of calculus, you have antiderivative apply on derivative. So again, if little f is a continuous function, then you have the integral from a to b of f of x dx is equal to, let's say you have the antiderivative capital F of x evaluated at a and b. This is calculated using capital F of b minus capital F of a, where capital F is the antiderivative of f. So, that is f prime is equal to f. So even though it's not really show that connection between derivative and antiderivative, it gets hidden inside this little f. That is little f equal to capital F prime. Okay, and so you have antiderivative apply on derivative. Again, they tend to cancel out, even though it's not mathematically correct to say that, but it's very convenient for us to understand the process. When you have that, then you have the function capital F back, and then evaluate that function at a and b. You get the second part of the fundamental theorem of calculus. So antiderivative of some common functions, and you have columns here. So the first column or the third column is some setup for antiderivative, and then of course on the second column, the fourth column, you have general antiderivatives. Because it's called the general antiderivatives, the solutions you get is called the family of function because you have the plus c at the end. You don't know the exact value of the plus c. That's why that plus c is called the arbitrary constant. You don't know the exact value of that. And when you get to the solution technique of differential equation, you will get some general solution or general antiderivative as well, because you don't know the exact value of c. But in addition to what we see in the general antiderivative, we will encounter something called the initial value or the initial conditions. With the initial values or initial condition, it will give you the exact value of c. Okay, so we get to that later, of course. So what is the initial value, initial conditions? For example, you drop a ball, right? You have a ball up here, you drop it. The initial velocity is 0 because you just drop it. Right? In another case, if you have a ball and you want to throw it, if you want to give it the initial velocity, then with that initial velocity, you have a different value for c. Okay, again, we get to that later. But for now, the general antiderivative of k is going to be capital F of x equal to kx plus a constant c. Again, c is the arbitrary constant. The antiderivative of x to the power n, given that n is different from -1, is going to be x to the power n plus 1 divided by n plus 1 plus a constant c. Again, n is different from -1. The antiderivative of 1 over x is ln of absolute value of x plus c. Antiderivative e to the x is just e to the x plus c. Antiderivative of a to the x is a to the x divided by ln of a plus a constant c. Antiderivative of sine of x is negative cosine of x plus a constant c. Antiderivative of cosine is sine of x plus c. Secant square, antiderivative of that is tangent of x plus a constant c. Antiderivative of cosecant square is negative cotangent x. Antiderivative of secant x times tangent x is secant x plus c. Antiderivative of cosecant cotangent is negative cosecant x plus c. Here you also encounter inverse trigonometric functions. So antiderivative of 1 over square root of 1 minus x squared is arc sine of x plus c. Antiderivative of 1 over 1 plus x is arctangent of x plus c. And the last equation is for the arcsecant. Now for integral technique or integration techniques, you learn about integration by substitutions, integration by parts, and integrations involving partial fraction decompositions. I'm going to quickly go over the first two integration techniques. Integration involving partial fraction decomposition, you're going to see a lot of this when we get to Laplace transform and inverse Laplace transform. So I'm just going to give you the formula here. We will talk about the details of this again on the integration involving partial fraction decompositions when we get to Laplace transform. Okay. For integration by substitutions, this is antiderivative process, right? And this is the reverse process of the chain rule that you see in derivative. What you do is that if u is equal to g of x is a differentiable function and f is continuous on an interval, then you have that and the integral of f of g of x times g prime of x dx is equal to f of u du, because u is equal to g of x. And when you take u equal to g of x, you take derivative on both sides, you have du equal to g prime of x dx. And therefore, you change the variable from x to u, where u is equal to g of x and du is equal to g prime of x dx. Okay, so that's integration by substitutions. Now, integration by parts, make use of the product rule for differentiations. Right? So again, this is the reverse process of product rule that you see. So the product rule you see of differentiations, f times g prime is equal to f prime times g plus f times g prime. Now for indefinite integral, you have the formula of the form f of x times g prime of x dx is equal to f of x times g of x minus the indefinite integral of g of x times f prime of x dx. That's the formula for indefinite integral. For definite integral, so indefinite integral, that means you don't have limit of integrations. For definite integral, you have limit of integration going from a to b of f of x times g prime of x dx. This is f of x times g of x evaluate at a and b, minus the integral from a to b of g of x times f prime of x dx. And the above integral is done by writing as follows, right? You let u equal to g of x, and therefore you have du is equal to g prime of x dx, and v is equal to f prime of x dx, or dv is equal to, this is dv, and this is v, is equal to f of x. And probably the following formula is what you see most of the time for integration by parts. That is, integral of u dv is equal to u times v minus the integral of v du. And the choice of U and V depends on the rank of functions that you encounter in the product, in the integral. Right, you follow this abbreviations, the at. Right, so for L is logarithmic functions, I is for inverse trigonometric functions, A is algebraic function, T is trigonometric function, and E is exponential functions. So let me quickly write that down. So L is logarithmic. Right, so it has a highest rank. So you let U, when you see logarithmic functions and algebraic function, you let U equal to logarithmic function. When you have algebraic function and exponential function, you let U equal to algebraic function, right? So L is logarithmic function. I is inverse trigonometric functions. A is algebraic functions. So algebraic functions can be x plus 3, x cubed minus 2x, something like that for algebraic functions. T is trigonometric function. And the last one is E, exponential function. Okay. So that's it for integration technique. Again, I will talk about integration involving partial fraction decomposition again when we get to Laplace transform. And that's it for this lecture, the lecture 0. We talk about kind of, again, higher informations of the techniques and the concepts that you learn in Calculus 1 and Calculus 2. So let me stop right here for the first lecture, or lecture 0, and move on to lecture 1 when we talk about introductions to differential equations.